Okay, so here's the exam review for exam 2. The exam is this Thursday during the regular class time. Exam resources are all online on my website. The homework solutions for homework 8 are also available on the website. So let's get started. I'm going to go through some of the questions I got in email. So we're about 30 seconds in. I'm going to talk first about the questions from Chelsea. Chelsea asked if I could go over stuff with statements equivalent to the Euclidean parallel postulate. So I figured let's just go through the solution to problem 2 from homework 8. So let's do that. Swap to this, go to that. All right. So homework 2. Homework 8, problem 2, said, prove that the Euclidean parallel postulate is equivalent to the following. If L and L prime are parallel lines, T is a different line, so that T intersects L, T must also intersect L prime. So this is saying that we've got, we want to show this is equivalent to the Euclidean parallel postulate. So what does that mean? That means we have to do two things. We have to first show that if the Euclidean parallel postulate is true, then this statement is true. Oops. That's going to happen quite a bit. This statement is true. And we want to show that if the statement is true, then the Euclidean parallel postulate is true. Right? So let's look at this first thing first. Assume the Euclidean parallel postulate is true, show the statement has to be true. So that means what we're going to assume is that if you have a line and you have a point, there is exactly one parallel line passing through that point. So what is it that we have to show? We have to show that if L and L prime are parallel lines, so let's start with that. Assume L is parallel to L prime, and we have another line T which is different than L, such that T intersects L prime. Oops, sorry, T intersects L. So, there we go. T intersects L. I need to show that T has to hit L prime as well. So I've got L, I've got L prime, and I've got some line T which hits L. Right? What I need to show is that this line also hits L prime. Well, how can I do it? Well, T intersects L, right? So there's this point P where they intersect. So what are we assuming? We're assuming that the Euclidean parallel postulate is true, right? So what does that mean? If T does not hit L prime, right? We're trying to show that it does hit L prime. Well, if it doesn't hit L prime, what has to be true? Then, by definition, that means that T is parallel to L prime. But there's our problem already. We're already at the issue, right? We are assuming that the Euclidean parallel postulate is true. So what that means is we, just make sure I'm on the screen, yeah. We're assuming that the Euclidean parallel postulate is true. That means that there's only one line which hits P and is parallel to L prime. Well, T is not equal to L, and T is parallel to L prime, right? We just assume that, and L is parallel to L prime, right? And they both, both contain P. And that's a problem. Sorry. You know how to do this. There we go. Zoom out. All right. There. Sorry about this. This is probably going to happen a few times. I apologize in advance. So this is a contradiction. All right. sorry. Right, there's my contradiction. There we go. Okay, sorry about that. Okay. So again, what did we show? We assume the Euclidean parallel postulate is true. Suppose we have the setup for the I want to prove that this statement is true. I want to prove that, this statement right here is true. Well, what does that mean? That means if L and L prime are parallel and T is different than L, and T is different than L and intersects L, I have to show something. So essentially what we're doing is you assume the Euclidean parallel postulate is true, and now the thing I highlighted here is your homework problem, right? Show that this statement has to be true. And that's what we did then. We proved this statement, and somewhere along the line we used the Euclidean parallel postulate, and we use it to say that this thing right here can't possibly be true. Okay? All right. There we go. All right. Now let's go the other direction. Assume this. So right, that's half of the problem. Start with the Euclidean parallel postulate. Assume that that is now floating around in space in the background, and now we just prove this other thing. Now what we need to do is assume the statement holds. Right. Assume the statement. And now I need to prove the Euclidean parallel postulate. Okay? How can I prove the Euclid? This is the thing I need to prove, the Euclidean parallel postulate. So what does that mean? That means we're going to take a line L, and we're going to take an external point P. So I got my line L. I got my point P. And now I need to show that there's exactly one line containing P, which is parallel to L, right? This is what we're showing. We now assume that that statement is floating around. We have it true, and we need to prove the Euclidean parallel postulate. The Euclidean parallel postulate is now my homework problem, right? So how do we do this? Well, we start it the same way each time. By the double perpendicular construction, we know we can build a line M with a transversal T so that this relationship holds, right? We have a line M which is parallel to L, and that's actually all I'm going to need in this construction, right? And P is on this line M, right? Oh, sorry if this upper right corner went behind my face. It just says prove Euclidean parallel postulate. That's all it says. I forgot that my camera's up there in the corner. Let me shrink my face a little bit, just so it doesn't get in the way. There. Okay. All right. So the double perpendicular construction says I can build a parallel line. So what I need to do now is show that this is the only parallel line. Well, if M prime is another line which hits P, right, and is parallel to L, that's M prime right there. Sorry. So I've got two lines now that are parallel. Well, what do we have? I need to show that this can't happen. Well, somewhere along the way, I have to use this statement that I've assumed, right? Somewhere along the way, I have to use the fact that if L and L prime are parallel lines, T is different than L, and T intersects L, then T also intersects L prime. Well, let me just use that statement. M prime, right? Let's assume M prime and M are different. This is a line which is different than M, but intersects M. So M prime hits M. Right? They hit each other And we've assumed that M is parallel to L at the beginning. So by our statement, by assumption, the assumed statement, that means that M prime, M prime hits M and M is parallel to L. That means that M prime hits L. And that can't happen. It can't be true that it's both parallel to L and hits L. So somewhere we have to use this statement, right? And it's just right away we're going to use it. Right? So some advice for solving these kinds of problems: whenever you're trying, what you do is just you essentially take it and split it up into two problems. One is, if the Euclidean parallel postulate is true, floating around there, prove some statement. And the other way is, if this statement is true, floating around in space somewhere, then prove the Euclidean parallel postulate. Well, the Euclidean parallel postulate, in order to prove that, we always just start with a line, right? Start with our line and a point. We can always construct a parallel line M using the double perpendicular construction. Right? We can always do this. And so just show that you can't have another line M prime. Okay? So that's the idea. Okay, so hopefully that made sense. The next problems come from Kelly. So 4.6, so this is about 12 minutes in. And we're going to, she asked about 4.6.3, so some stuff about quadrilaterals. To answer a different email question, yes, quadrilaterals are on the exam. So 4.6.3 says, talks about an alternative definition of a convex quadrilateral. Okay. So we're going to say that a quadrilateral is semi-parallel, according to this definition. A quadrilateral is semi-parallel if, or the opposite sides of a quadrilateral are semi-parallel if the segment never hits the other line. Right? So what's that mean in terms of a picture? It means that if I've got a quadrilateral, whatever, A, B, C, D, then if I extend out this line CD, right, we're going to say that A, B, and D, C, D are semi-parallel if when I extend out this line CD, it never hits the segment AB. So we're not saying they're parallel, we're saying they're semi-parallel. The line never hits the segment, right? That's the definition here. And also vice versa, that if I drew out this line AB, it would never hit the segment CD. Okay, so the problem asks us to show if one pair of opposite sides is semi-parallel, then the other one is. So let's assume that the top and bottom are semi-parallel. Right? We need to show that the left and right are semi-parallel. Okay? So, what if this didn't happen? Right? We need to show that AD and BC are semi-parallel. Right? And what that means is that we need to show that AD intersect the line BC is empty, meaning they never hit each other, empty. Right? And vice versa, we need to show that BC intersect the line AD is also empty. But we can do one of these and the other one will be very similar. Okay. So what if AD hits the line BC somewhere? What does that mean? That means the left-hand side, so the segment AD, would have to hit the line BC somewhere. So what would that look like? That would mean, like, I've got my segment AD here. I've got my line BC, which I extend out this way, and or this way. Oops, that's not what would happen. Let me draw this. So again, what if we got a picture like this, right? So why would the picture look like this? We're assuming that the segment AD hits the line BC somewhere. A, B, C, D. Right. Let's say this is our picture. Let me relabel it just for, so it looks like what I had before. A, B, C, and D. There we go. Whatever. Same thing. We've got our line BC, which hits AD somewhere. Right? That means I've got this point P where it hits. Right? So we're assuming that. Well, what does that mean? That means if this ray hits this side, then let me look at the big angle right here, ABD. That means BC is between BA and the ray BA and BD. Okay. So BC is between BA and BD. That tells me that A and C, the points are on the same side of the line BD. Right? That's what I've got, right? In other words, I've got these 2 points here. What I'm trying to show, what I'm trying to get at now is, okay, I've got BC, the line BC hits AD. I also need to show then that this line DC would have to hit the line AB. Right? If this kind of thing happens, then I need to show that this happens, right? Because we're assuming that this doesn't happen. We're assuming that AB and CD are semi-parallel. We're assuming that this segment and this line never meet. Well, what I need to show then is if this segment AD and this line BC hit, then I can also conclude that the segment AB and the line CD have to hit each other. Okay, so what do we have? We have that A and C are on the same side of this bottom side of the angle I drew. Let me switch colors. I can also say, let me look at this segment BC. I know that BC can't hit the segment AD. That is part of the definition of a quadrilateral. Two sides, like the two opposite sides of a quadrilateral, can't hit each other. We can't have a picture like this, remember? So we know that BC, the segments can't hit each other. So in particular, the intersection point that I drew, point, let me call it P, this intersection point between the ray and the segment, between the line and the segment, this intersection point P is not on the segment BC. Right? That's all I'm saying. I'm just saying that, sure, BC, the line BC has to hit AD. I know it can't happen on the segment, so what this tells me is that B and C are on the same side of AD. So what do I have? I have A and C are on the same side of BD. I have B and C are on the same side of AD. So let me just redraw this picture now. What have I just shown? So here's my figure again. A, B, C, D. If I look at, let me draw in orange. If I look, I have shown that B and C are on the same side of AD. I've shown that A and C are on the same side of BD. So what that tells me is that C is in the interior of angle ADB. And that's a problem. Because then according to the crossbar theorem, right, according to the crossbar theorem, we have that this ray, if I draw this ray, DC, it's got to hit AB. The ray DC hits the segment AB, and that can't happen. Bad. Actually bad, not anything with an angle. This is bad because we assumed that DC and AB are semi-parallel, right? Semi-parallel. Right? So there's our contradiction. We've reached a contradiction. We've shown that if one pair of sides is semi-parallel, then the other pair of sides has to be semi-parallel, right? We reach a contradiction by assuming they weren't semi-parallel. We haven't end up getting semi-parallel. Okay, so that's what we were trying to show. If one pair of sides is semi-parallel, then the other pair of sides has to be semi-parallel. Okay, so about 22 minutes. Actually, part B is very similar. And also, Kelly asked both about part B and about number 4. So part B and number 4 are very, very similar to each other. So just to address those problems, we want to show that ABCD is convex if and only if both pairs of opposite sides are semi-parallel. Right? So I want to show that something is I want to show that this thing is convex if and only if both sides are semi-parallel. So let's start. I'm going to do this with a picture rather than getting bogged down in the details, just to move on to some other stuff. If I have a segment, a quadrilateral which is not convex, right, like this one right here, what would have to be true? If it's not convex, what does that mean? That means one of its vertices, remember, convex means if you have a quadrilateral, that's a D, every vertex lies in the interior of the opposite angle, right? That's the definition of convex. So if we have something that's not convex, what that means is one of these vertices, let's say D, assume D is in the interior of angle BAC. Let's say that happens. Let's say D lies in the interior of angle BAC. So a different color. Let's go with red. That means if I draw the angle BAC, D is inside of it. Right? Well, what's wrong with that? Well, that means that this line DC, wrong line. That means that if I take this ray AD and extend it out, it's got to hit the segment BC. Okay? That means the ray AD hits the segment BC. And what name did we give that? We called that the crossbar theorem. So we called this according to the crossbar theorem, if D was in the interior of the angle, then the ray AD would have to hit this segment BC, right? If I draw this triangle ABC, that ray has to hit it. So, in other words, that would tell us that AD and BC are not semi-parallel. So if it's not convex, that means not semi-parallel. Right? So that's what I just showed. If it's not convex, it's not. We don't have semi-parallel sides. So what I need to show then is if it is convex, then the lines are semi-parallel. Well, I can go the other way. If the lines, actually, according to what we showed in part A, using the arguments that I gave you, those really gross arguments that I kind of stumbled through about 5 minutes ago, if the sides are not, if any pair of sides is not semi-parallel, if one of the pairs of sides is not semi-parallel, then you can draw the picture like I had before and argue using same sides and betweenness and all this kind of stuff to show that it's not convex. Right? If the lines are not semi-parallel, that means we have to have a picture that looks something like this. That means if I extended the line out, let me box it off. If I extended one line out, right? If we don't have semi-parallelism, that means if I extend one of the lines out, it's got to hit a segment somewhere. Well, if that by definition means that this point is in the interior of this angle by the between, one of the betweenness theorems for something, or by the definition of betweenness for rays. Right? So if I label this A, B, C, D, if the ray AD hits the segment BC, that means D has to be in the interior of BAC. But that's by definition means that my quadrilateral is not convex. Right? So if it's not convex, it's not semiparallel. If it's not semiparallel, it's not convex. Using that argument, we can say that a quadrilateral is convex if and only if it is semiparallel. Right? So that's part B of the problem. So a lot of the arguments here involving convexity just come down to talking about when points are between, rays are between other rays, or which points lie on which sides of lines. That's the idea there. Okay. Let's see. Kelly also asked about question 4. So 27, 30. I'm just writing down my timestamps like I do. I'll put them in the description of the video. We say that a quadrilateral is a trapezoid if either the top and bottom are parallel or the left and right are parallel as lines. So not semi-parallel, but parallel as lines. So I need to prove that every trapezoid is convex. And the argument here is going to be very, very, very similar to what we were just talking about. Right? So let's say I have a trapezoid. Right? So let's say I have AB and CD. If I were to draw these lines out as lines, they would be parallel lines. So let's see, why does this have to be convex? We'll do this contrapositively. We'll go backwards. Let's assume it's not convex. Assume my picture looks something like this. A, B, C, D. Well, then we can go about the same kind of arguments we had before to show that AB and CD. Well, okay. Let me just say what I'm doing. So let's say again, assume ABCD, this quadrilateral ABCD is not convex. And what does that mean? That means we'll say that maybe D is in the interior of angle BAC, like I have in this picture. So if I look at this angle BAC, D is in the interior of it. So what that means is, in particular, if I extend this ray out, according to the crossbar theorem, once again, similar arguments as before, tells me that the ray AD has to hit the segment BC. Fine. So in particular, AD then is not parallel to BC. Okay, fine. AD is not parallel to BC, but what about the other sides? What about AB and CD? Right? What about, let me get a different color here, green. What about AB and CD? Well, I can make the same arguments I was making before. I know that D has to be in the interior of this angle, BCA. And the reason for that is because I know that the segment CD can't hit the segment AB. I know these opposite segments can't hit each other. And the fact that D is in the interior of BAC, I can start arguing these 2 points have to be on the same side of this line, these 2 points have to be on different sides of this line, blah, 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 to say that D also has to then be in the interior of BCA. And we can argue the same way, then, that CD hits AB. So that's the idea. So they can't be parallel lines. So I hope that makes some sense. I don't know why I did it like that. So they can't, oh, sorry. What am I saying? They can't be parallel lines. Oops. they can't be parallel lines. Right? So, in other words, A, B is not parallel to CD. And so that these two things together tell me it's not a trapezoid. So again, not convex means not a trapezoid, which means trapezoid implies convex. If it's not convex, it's not a trapezoid. Contrapositive said, if it's a trapezoid, then it's convex. Okay? So the arguments, problems 3 and 4 are very, very, very similar. So I understand why you asked about both of them, Kelly. Okie doke. So about 3230. Samantha emailed and asked, there it is. She asked a couple things for the video. One of them, she asked me to talk about interior, alternate interior, corresponding, non-alternating interior, exterior, remote interior angles, all that stuff. So all of these types of angles. All right. Well, the definition is if I have a line, if I have two lines, L and L prime, cut by a transversal T, what that means is the line T intersects L and L prime at different points. So in particular, I can come up with points A, B, and C, points A prime, B prime, and C prime. And if I want to talk about angles, I can now give names to all of these angles. So the alternate interior angles are the angles AB, B prime, and B, B prime, C prime. Those are the alternate interior angles, okay? Alternate interior angles are those, or CB, B prime, I should not, they're not necessarily the same, or CB, B prime, and this other one, B, B prime, A prime, right? So those are my two pairs of alternate interior angles. So it's the upper left and lower right, or the upper right and lower left, okay? Yeah, I wanted those. B prime and C prime. Okay, those are alternate interior angles. And what we know is that if some pair of alternate interior angles is congruent, then the lines are parallel. Okay. We don't have the other direction, remember. If they're parallel, I don't know anything about congruency, unless I say something about the Euclidean parallel postulate. Okay, so what else do we have? What are corresponding angles? Corresponding angles would be this one up here and this one down here. Right? Or possibly a pair of corresponding angles would be this one over here and this one over here. Or a pair of corresponding angles would be this one down here and this one down here. Whatever, however many lines I need to draw. Right, so corresponding angles are the upper right ones, the upper left ones, the lower left ones, the lower right ones. And the only thing we know is that if some pair of corresponding angles is congruent, then the two lines have to be parallel. And that just follows immediately from the alternate interior angles theorem. Just use the alternate interior. Use the fact that these vertical angles are congruent, and then we know that this pair of alternate interior angles is congruent, and so therefore the lines are parallel. Okay. So sorry, I didn't even say interior. Interior angles are just what we call this one, this one, this one, and this one. These are the four interior angles. And then we have pairs of alternate interior angles. Alternate interior, corresponding, non-alternating interior just means, so we don't really have an official name for, or I don't know if I officially define those, but non-alternating interior just means in the interior angles that don't alternate. So I had four to choose from. non-alternating interior are the ones on the inside which don't alternate. And then, so that's the idea. We have the alternate interior, we have the 4 interior angles, 2 pairs of alternate interior angles, 2 pairs of non-alternating interior angles, and then we have 4 pairs of corresponding angles, right? And then you also asked about exterior and remote interior. That's when we're talking about a triangle. If you have a triangle and I extend one of the sides out, this angle that I get is called an exterior angle for the triangle. And so we know something about the measure of that exterior angle. These 2 angles I'm drawing right here are remote interior angles. These are the remote interior angles associated with this exterior angle. And what the exterior angle theorem tells us, that thing from 4.1, I believe, tells us that if I've got a triangle and I extend out one of the sides, this exterior angle is strictly larger than either one of the interior angles, the remote interior angles, okay? So that's when we're talking about alternate interior angles and stuff like that, we're referring to this upper left picture. When I'm talking about exterior and remote interior, I'm referring to this triangle picture. Okay. All right. Then you asked, Samantha also asked about 4.4.8. So this is about 38 minutes. Proving corollary 4.4.8. So corollary 4.4.8 is going to be, not going to take too long. If L, M, and N are 3 lines such that M is perpendicular to L and N is perpendicular to L, then either the lines are the same or they're parallel. Okay. So we have M is perpendicular to L and N is perpendicular to L. So M, N, and L. I have this L right here. I have M, which is perpendicular to L, and I have N, which is perpendicular to L. Right. So it's perpendicular. All 4 angles here are perpendicular. So either M and N were the same line. Either my picture looks like this. M and N were the same line. If they're the same line, if M equals N, we're done, right? Because that's one of the possible conclusions. If M is not equal to N, then what does that mean? Then L is a transversal. Right? L is a transversal for M and N. And what do we know? It's a transversal with congruent alternate interior angles. All of the angles in this picture are right angles. So in particular, if I look at some pair of alternate interior angles, they're right angles. They're congruent to each other. And according to the alternate interior angles theorem, I can therefore say that M has to be parallel to N. Let's try that again. M has to be parallel to N. Okay. So I hope that makes sense. That's corollary 4.4.8. So it's just to use the alternate interior angles theorem, and it works. All right. Then her next question was regarding these statements equivalent to the parallel postulate. This is about 40-30. So some statements equivalent to the parallel postulate. In particular, you asked about one direction of 4.7.4. So you didn't exactly ask this, but this is what your question was. 4.7.4 is prove the third statement of 4.7.3, that is, prove this guy right here. Okay? If you've got 4 lines, L, M, N, and K are lines so that K is parallel to L, M is perpendicular to K, N is perpendicular to L, show that either the lines have to be the same, M and N have to be the same, or they have to be parallel. So this one's a bit longer than the other ones in this same kind of thing. But what we want to show is that this is equivalent to the Euclidean parallel postulate. So Samantha particularly asked about if we assume the Euclidean parallel postulate, then we have to show this. This statement is not true in general. Right? The statement is not true in hyperbolic geometry. But if the Euclidean parallel postulate is true, so let's assume the Euclidean parallel postulate is true, I want to show the following. Okay, so I've got K and L are parallel lines. I have M perpendicular to K, and I have N, which is perpendicular to L. Then either M is equal to N. If M is equal to N, we're good. We're done. Fine. That's one of the things we want to show. If M is not equal to N, what we want to show is that M and N are actually parallel lines. So what I need to do is use the alternate interior angles. Or sorry. I don't use that. What I need to use is the Euclidean parallel postulate somewhere. I'm assuming it's true. This statement is not true without the Euclidean parallel postulate because possibly my lines, L maybe trails off down here and M trails off up here, and then maybe M and N bend in and hit each other somewhere. So I don't exactly know, or maybe all the other lines go up and these lines go down. My lines aren't straight. I can't just continue L and say, oh, this is definitely perpendicular. So I need to show that M is parallel to N. Right? And I need to use the Euclidean parallel postulate somewhere. Well, let me use it right away. Let me look at this line L right here. If this was hyperbolic geometry, I wouldn't be able to say necessarily that L hits M. It might be that L might bend off down here and they become asymptotically the same, or maybe L bends up with M. But since I'm in Euclidean geometry, I'm okay. According to the Euclidean parallel postulate, by the Euclidean parallel postulate, what do we have? We have that M, what am I trying to say? Sorry. I have this parallel line, there we go. I know that K is parallel to L. And there's this point P in M intersect K, right? I've got a point at which M and K meet, right? M and K are perpendicular, so they meet at a point P. Also, I know that K is parallel to L. Well, what that means, according to the Euclidean parallel postulate, that means that M cannot be parallel to L, right? Euclidean parallel postulate tells me there is exactly one line which hits this point P and is parallel to L, and that one line is K. Well, that means M is not parallel to L. That means if I draw out this line L, it's got to hit M somewhere. This does not happen in hyperbolic geometry, but since we're assuming the Euclidean parallel postulate, I can just extend this line L, it's got to hit M. Similarly, same kind of argument, I know that M cannot be parallel to, what was this one? This is K, sorry. I was like, my labels are off. K is not parallel to N. Oops. K is not parallel to N. I know that these upper right corner, we have to have an intersection there. Okay. So let me redraw my picture. What's the picture I have now? Maybe I can edit that out for the final video. So sorry, I'm restarting this. I just edited something out. Hopefully the editing worked. So I've got M, N, L, and K. I just need to show that, so like I said, I just need to show that one of these guys is a right angle. Okay. So how do I do it? I've got this point here, Q, at which L and N intersect, right? I just assume that there is some point of intersection. And what if this is not a right angle here? Well, I can draw a line L prime, if that's not a right angle, I can draw a line L prime such that L prime is perpendicular to N at Q. So there's my line L prime. L prime. And now this guy is perpendicular to N. Well, since it's perpendicular to N, that means, so L prime is parallel to K. Alternate interior angles theorem tells me that this new line I just drew has to be parallel to K. And it's perpendicular, so L prime is going to be different than L, since I'm assuming that this angle is not a right angle. Well, that's a problem. This can't happen because we assume the Euclidean parallel postulate is true. I assume the Euclidean parallel postulate is true, so I can't come up with this perpendicular line L prime. That perpendicular line doesn't exist, right? So, that means, that is, I have this picture. I had this right angle, I had this right angle, and I actually do have a right angle up here. So by the alternate interior angles theorem, M and N are parallel. So like I said, this one was longer, definitely, than the other ones in this same theorem. This one was definitely longer than the other ones in the same theorem. I had to use the Euclidean parallel postulate twice. Actually, the problem would be easier if I could just cite some of the other parts of the same theorem. But yeah. So hopefully the argument made sense there, and hopefully I was able to edit out my mistake. So the last question that Samantha had, and the last question that I'm going to cover, is how is convexity related to parallelism? Well, if you look at 4.6, you get a whole bunch of answers for that. Essentially, when you have opposite sides of a quadrilateral being nice and parallel in some sense, then you know that the quadrilateral has to be convex. Right. So that's the idea. If you know that the lines are parallel in some sense, then the quadrilateral is going to be convex. And the way the proof of that is, if you look at theorem 4.6.6, every parallelogram is convex. Or problem 3 that we talked about earlier, if they're semi-parallel, the opposite sides are semi-parallel if and only if the quadrilateral is convex. Or the quadrilateral is a trapezoid. If it's a trapezoid, then it's convex. So there is a very strong relationship. There's no definition relationship that makes them the same, but there's a very strong relationship, and it all comes from these arguments with interiors of angles and rays being between other rays and points being between other points. Okay? All right, so hopefully that all made sense. And that's all the questions that were emailed to me. Let me go full screen. That's all the questions I got. So if you have any more questions while you're studying, feel free to send me an email. I'll be flying back from Poland on Thursday, but I'll have internet access on Wednesday. I'll be in a hotel Wednesday night, so I can answer emails then. All right. So if you have any questions, send me emails. Good luck on the exam. Yeah. That's it. Good luck.